All right, good morning. Let's see, quick question has come up. Why does the order of the fields matter? If the explanation is too long, don't worry. Yes, excellent question. Let's talk about this. So I don't know if you've taken Engineering 270 yet, but that helps a little bit with this. So suppose, well, let's just jump into it here. Okay, so I'm going to write some code here. Cool. All right, I'm back. Yeah, good morning. Thank you for letting me know before I went on for like 10 minutes. All right, so let's do a simplified case of this. So I'm going to make a struct node. I'm going to make an integer a and an integer b. And I'm going to say struct node new equals, just going to do a struct node new, and I'm going to say my print node. All right, so there's a struct node. It's got two fields A and B. I'm going to have a main program that calls a print function and passes that node. I'll be polite and prototype my function. And then let's write my myPrint function. And in here I'm going to do my nodes in a different order. And I'll print out data A and data B. And over here, I'll set A equal to 111 and B equal to 222. And I'm going to call my print function, and my print function should print out the values of A and B. All right, so just a basic example of setting up a pair of functions that share a structure. Oops. I haven't done Java in a long time. I'm not sure why my brain went to Java. Node undeclared, line 13. Too many variables with an n in it. All right, there's my function. Let's go ahead and run it. And, you know, as we expect, it messes up. So A is equal to 222, B is equal to 111. All right, so what's going on here? So let's compile with GDB. All right. So we're going to set A equal to 1, 1, 1, and we're going to set B equal to 2, 2, 2. So if we print if we print new, it's got these values. If we print the address of new is stored at FE408. Alright, so I'm going to make my memory map here. So this is where the structure new is stored, E408. And at that location we find new.a. So new.a is stored at E408, right? So I'm putting that in my memory map. And if we print the address of new.b, that's 4 bytes later. That's E40C, new.b. So this is what my node looks like in memory. All right, let's go ahead and let's make a call to the myprint function. So now I'm inside myprint and I passed in something called data. And if I print out data, it's got these backwards values. Why is that? Well, let's print the address of data. Data is stored at E3, E8. That's where data is stored, right? Because we pass by values. So data is a separate variable, but it copied the values from new into data. But let's look at the address of data.a. Data.a is stored at E3, EC. And if we print the address of data.b, that's E3, E8. So here's how memory has been set up by the compiler and the linker. Right? In our main program, we had a variable new. It stored new.a at 408, and it stored new.b in the next location. In our function, myprint, right, the compiler stored data.b at E8 and data.a at the next location. Right? Why did it do that? Because in my myprint function, that's the way I wrote the declaration of the struct node. Now when the code is running, we've got ones and zeros in memory, the CPU's pulling them out and executing them. And it says, hey, you want to pass this variable new to this function myprint. All it does is take these 4 bytes, copy them there, take these 4 bytes, copy them there. And the effect is, in my myprint function, when I ask for data.a, I'm looking at a value that was copied from new.b. So the essence of the problem is, right, the notion of .a, .b doesn't exist when we're running the binary code. When we're running the binary code, all we have is what the compiler put together, which said, hey, if you want data.b, that's the address of, that's stored in the beginning of this structure. If you want data.a, that's stored 4 bytes after the beginning of the structure. Why does it think that? Because that's how I wrote the struct statement in myprint. So it has no way of knowing that this thing that's 4 bytes after the start was the thing that was at the beginning of this new structure. It's really just looking at displacements from the beginning of the structure. So it's a different memory map basically in myprint because of how I wrote the structure statement. I don't know if that helps or not. It's passing the correct values, but and they're being stored. The first 4 bytes of the thing being passed are being stored in the first 4 bytes of the argument. The next 4 bytes are being stored in the next 4 bytes. That's all perfectly fine. It's just that the code that is inside myprint thinks data.a is stored 4 bytes after the start of the structure. All right, cool. Nice. Other questions? So if you call data.b first, there wouldn't be an issue, right? So in my right, if I had done integer b, integer a in here, that would be fine. Or if I passed, you know, new.a and new.b as two arguments, and I picked them up as two separate arguments in my print function, that would take care of the issue, right? But as a structure, we're trying to pass a bunch of things as a single entity, and how does that work? Well, we basically just pass the address where all of these things are stored, the starting address, for some chunk of memory containing multiple things. But what's the meaning of those things? What's at the first location, the second location, and so on? That's up to the structure statements declaration. Was there an example of PA1? I know I debated putting that up. Nope, I didn't post an example of PA1. But yeah, we did go through it in class. Consistency in struct statements is important, right? That's a good punchline. Consistency in life can be important, but sometimes inconsistency is even more valuable. I'm thinking in terms of art and poetry. All right, cool. Other questions? All right, let's do some sample code. Let's cobble together some pieces of things that might help you with PA1. This is not going to be PA1, obviously, but let's write some code. Writing code is usually a good thing to do. So. And I want to do this partially to show you some code, but also to show some examples of working with your code as you're developing it, including, you know, getting into GDB to look at some of this stuff and playing around with debugging and so on. So so let's just have some fun with this. So struct node, we'll make 100 struct nodes. I'm going to put my initialized code right in here in main, right? So don't do this, don't follow this and say, well, that's what you did in class, right? I'm doing a really kind of sloppy, quick and dirty, going way outside the lines kind of exploration of this linked list built in an array of struct nodes. So for example, I'm just going to do my initialization right here. So my null is a 0, which is going to be what I use anytime I'm dealing with a next field. I'm never going to check to see if next is equal to 0, if get node returned to 0, etc. I'm always going to use my null. So I'm going to set my sentinel node to be valid, just so I don't have to think about that. I don't need that. I'm going to set the next field to be my null. I don't even need to worry about the valid bit. And all the other fields I'm going to set valid equal to 0. Okay. While I'm in here, I'm going to write a getNode function. Alright, so there's my getNode function, which loops through, starting at index 1, because we don't want to reallocate the sentinel, right? And goes up through and including 99, and checks the valid flag. If the valid flag is 0, this node is free. So we set the valid flag to 1, we return its index. We're not going to run out of memory in the work we're doing, but, you know, just so I can sleep at night. If we come out of the for loop, we'll return my null, showing that that we're out of memory. I'll prototype this. All right, so this should work, right? See how badly we did. I forgot my closing bracket because I wrote my getNode in the middle of thinking about things. Alright, so we're good so far. Alright, so we've initialized an empty linked list. Let's run this in the debugger and see what's going on. So we're going to do our initialization, which is going to take a while. Oh, I guess it blew through it. Okay, so we're at the point where we're going to say goodbye. Let's take a look at our linked list. So if I print LL, here's what LL looks like. Okay, it's got a lot of stuff in it. It's an array, and print in GDB, if you have an array declared with brackets, it'll show you, you know, the contents of it. All I care about, though, is the first element in my array, which is this right here. And it's showing me that the next field is equal to 0. That's what I wanted to have set up. Okay. My initialization didn't work. I messed up something somewhere. Because in my other nodes... Oh no, that's fine. My valid flag is set to 0, right? The data value is you know 2 to the 15th minus 1. The next value is some big integer, but the valid field is 0 in all of these nodes. Okay, that's what the purpose of the init function was. So we're good so far, right? So I don't want to display all of this, so I'm just going to hit a Q to quit that display. And our code doesn't do anything else. So let's develop our code a little further. Let's write an add method. And this is just going to add something to the very beginning of the list. All right, so pictures. I'm not going to try to correct typos anymore today. All right, so here's our sentinel, which always exists, but we don't consider it to be part of our list. And this, you know, might be my null if we're starting with an empty list. If we have stuff in our list, then the sentinel points to, you know, some data value D1, and this points to some data value D2, and so on. All right. Yes, don't correct typos Wednesday. Excellent. All right, so let's just add something to the beginning of the list. Let's write something so that if this is what my list looks like, it puts a new node right here before what's currently D1. All right, and if my list is not empty, I'm going to create a new node. So here's new. I'm going to load the data value accordingly. And then I need to do two things in order to insert this in the beginning of the list. So the first thing I need to do is have the sentinel point to my new node. And the other thing is I need my new node to point to, in this case, D1. All right, so two things that have to happen. Have the sentinel point to our new node, have our new node point where the sentinel used to point. All right, well, let's put some names in here. Here's our sentinel. Let's call this thing first node. We'll call this thing new node. And let's just go ahead and set these things up. Okay, so let's make an add function. Gotta embrace my typos. Okay, so integer integer new node equals get node LL. Right? What are we doing here? We're going to call get node, and it's going to tell us where in our array we can store this new node. So new node is an integer, right? I'm thinking of it as a node, but it's actually an index into an array of nodes. And if I looked at LL bracket new node, right, that would actually be the node. But this is this convention that I've mentioned is going to sometimes be confusing, right? First node is going to be an integer, but I'm going to think of it as a node. I'm going to write it on top of a node as if it's actually a node, but it's not. It's just a plain old integer. But what it actually is an integer, which is the index where in my linked list array that node is stored. Okay, so that can be confusing, but embrace that confusion, right? Because we want those two concepts to merge. We want to think of this as an actual node, even though it's just an integer. It's just an index in an array. If you can think of it as being the node in some sense, coding gets a lot easier with this stuff. And that will absolutely carry over to PA2 and all the other assignments. So it's a good sort of confusion. All right, so new node equals get node LL. This is actually the index of the node. So LL bracket new node is the node itself. All right. So let's save the data value. New node.data equals data. So that's loading in this field here. And let me set up an integer for first node. So integer first node equals LL bracket index 0. That's the sentinel node. Dot next. So that's what the sentinel points to. So that's this node right here. All right. So let's write our two statements. To set up this arrow, what do we want? We want new node next should be first node. All right. We want this thing's next field to be first node. Well, new node is not a node. It doesn't have a next field. It's an integer. But here's what we actually do. LL bracket new node dot next equals first node. So that causes the new node to point to what was originally the first node. Alright, so this is that part where I've said before, don't worry about the code, worry about why we're writing this statement, right? All we're trying to do is make this little arrow here. So LL bracket new node is the actual node. It has a field called next. We set that equal to the index of what's currently the first node in the list. That leads us to the statement LL bracket new node dot next equals first node. And then the other piece of this is we need the sentinel to point to our new node. Well, the sentinel is always stored at element 0. So it's just LL bracket 0 next equals new node. And that should do our insertion in the beginning of the list. Alright, again, new node is an index. So LL bracket new node dot data equals data. Now you can get around some of this by declaring struct nodes. I could have made you know, a struct node called first node and a struct node called new node instead of making these integers. You could do that. All right, so let's do some stuff. So let's add some things to our list. So we're going to call our add function a few times. We're going to add 10, 20, 30, and 40. So we're going to do our for loop. We're going to initialize our sentinel. We're going to add a 10, add a 20, add a 30, add a 40. And now we're done. So let's take a look at our linked list. Well, I see some 10s, 20s, 30s, 40s in here. That looks good. Let's see what this is saying. Our sentinel node says next equals 4. So the first node of our list should be stored at index 4. Okay, this is index 0, 1, 2, 3. Here's index 4. There's a 40 stored in the beginning of our list. And the 40 says the next node is at index 3. Well, index 3 is right here. There's a 30 stored in our list. and that says the next node is stored at index 2, and index 2 is the 20, and that says the next node is 1, which is this node right here, which says there's a 10, and the next node is my null. So by looking at this data, my sentinel points to a list comprised of 40, followed by 30, followed by 20, followed by 10. And that's exactly the right thing, right? Because our add function is inserting at the beginning of the list. So we insert a 10, then we put a 20 before it, and then a 30, and then a 40. So this is not a lot of code, right? I've got probably more comments than I have actual code. Get node you've already written, right? The simplified add function, right? But this is basically what you want to do, but somewhere in the middle of the list, depending on the number that you're inserting, right? Oh, but let me go back and look at this, right? So what about the case where our list is empty? What if our list is empty? We're going to create a new node. And in this case, first node is going to end up being equal to 0. Because first node is, the thing that sentinel points to, it's going to be my null, which we know is 0. But, I'm going to load the data value in, same as usual. And then when I say new node next equals first node, what's that going to do? It's going to set new node next equal to my null. And then when I set sentinel to be equal to new node, that's going to set up this pointer. So if I'm starting with an empty list, those same two statements will successfully add a new node right after the sentinel. So in this case, we don't have a special edge case, right, for inserting at the end. And the sentinel node basically is there to eliminate edge cases or reduce the number of edge cases. Now, there's nothing wrong with explicitly handling edge cases. If sentinel next equals my null, then let's do something different. That's perfectly fine. But think about it. When you've got your general algorithm, see if you actually have an edge case, because sometimes you don't. And simpler code is usually going to be better to work with down the road. All right, so this is a simplified add function. Let's make a print function. So let's just traverse the list. All right, so how are we going to traverse? We're going to have our sentinel. It's going to point to a node. It's going to point to a node. And let's say this is my null. All right, how do we traverse? Well, we want to start with this node, print out its data value, follow its link to the next node, print out its data value, follow the link to the next node, print out its data value. When we try to follow the link to the next node, that'll take us to, that'll tell us it's my null. We're done printing out values from the list. So I'm gonna, have some variable current, which I'll use to represent the node, the index of the node that I'm about to print out. So I'm going to print ll bracket current dot data. And I'm going to set current equal to current next, which for us is ll bracket current dot next. And I'm going to do this in a loop. All right. So the two main questions with a loop: how do you initialize? How do you get out of the loop? Those are edge cases, right? But once we're in the loop and we're rolling along, right? Say this is what current is pointing to. I'm going to print out current node's data. I'm going to set current equal to what current is pointing to, which will move it here. I'm going to print out current node's data. I'm going to set current to what current is pointing to, which will change it to here. I still want to print out current node's data. I'm going to change current to what it's pointing to, which means current will be now my null, which is not a valid node. That's where I want to exit. So that makes me think I'm going to do all this while current is not my null. The other question, how do we initialize this? Well, we want current to start off being the first node, which means, you know, current equals whatever the next field of the sentinel node is. And what happens if my list is empty? Well, when I initialize current to what the sentinel is pointing to, it's going to be equal to my null, and my loop's not going to do anything. So here again, we're not going to have any special cases for an empty list versus a non-empty list. Alright, so let's see what this looks like. So I'll set current to the sentinel node's next field, which means it's either the first node in the list or it's my null if the list is empty. I put a semicolon after my comment. That's kind of cute. Alright, while current is not my null, let's just print out the data. And then let's move down the list. So current equals LL bracket current dot next. So move down the list. Does this look reasonable? So set current to the first node of the list. As long as that node exists, as long as it's not my null, print out its data field, and then move to whatever that node is pointing to. So there's your list. Now if your print function is if your print function is not doing the right thing, right, put a breakpoint in there and run until you get into your print function. Okay, we're in our print function now. Print function has been called with LL. If I print out LL, it's a pointer to a struct node, so it doesn't realize that it's an array yet, but that's okay. I can look at LL bracket 0, that's our sentinel, and I can see, you know, clearly what the three fields are. I can print LL bracket 4, that's the first data node, and the next field tells me the next node is at index 3. I can look at index 3 and so on. But we can run through our code, right? So current equals LL0 dot next. So I can execute that. and I can look at the value of current and see that it's 4. And that's not my null, so it's going to come in here and it's going to print LL bracket current dot data. If it's not printing the right thing, right, take a look at this. Or maybe take a look at this. Right, print out your 40 and then go on to the next node. So take a look at current, take a look at LL current, take a look at LL current next. Do this assignment, make sure that looks correct. But at this point, you know, we're down to the metal. We are able to explore our structure in gory detail, see exactly, you know, what's where and what's pointing to what and what's at that location that's being pointed to, and see how the code is analyzing and, you know, modifying those things in memory. And if you have a bug, you know, if you're printing and you're missing the first node in your list, for example, or you're not printing the last node, or you segfault when the list is empty, right? This is the level at which you will be able to discover what's going on. So suppose you do something like this. Right, suppose you wrote it like this. Alright, so current equals LL0 dot next. So let's execute that. And let's look at current. Current is equal to 4. There's our first node, that looks good. So we'll go ahead and we'll print out the 40. Here's our 30 node, we'll execute. There's our 30 that got printed right here. This is a little hard to see because my prints are unembellished. And now we're going to set current equal to LL current dot next. Well, current is 3. LL3 has a 30 in it, it's pointing to a new. Go on there and print out. There's our 20 being printed. Current equals LL current dot next. Here's LL bracket 1, so this is going to process the node 10. But we're at the end of our loop. We suddenly exited, right? And why did we exit? Well, let's look at LL bracket 1. Well, LL bracket 1 next is equal to 0. That's my null. And my while statement, the way I wrote it, said in that case we should exit. Well, it exited without printing this last node. So what do? You can go ahead and after your for loop, you can add something in that prints out the last node. But that's kind of a band-aid, right? The real problem is I exited this loop too early. So don't try to fix bugs. Try to understand bugs. Okay? If you try to fix bugs, you're putting, you know, more duct tape on top of something, and then you add some coat hangers, you know, and you put some more duct tape and some super glue, right? That's not the code you want to end up with. So my code is buggy. It's exiting my loop too soon. If I try to fix this by adding a statement here that says, okay, let's print out LL bracket current, I'm going to introduce a new bug. It's not going to work when I have an empty list. So the right way to fix this is change this and exit when LL current is equal to my null, right? So when you find a bug, right, pin it down, analyze it, understand it, and then go back and update your code to eliminate that bug, not to let the bug persist and add something else to try to deal with it. Right? So here's how you can get into trouble. right? Bug fix, let's print the last entry. Wow, I'm like in a weird, it's not quite Java, it's not quite C day. Right, so that looks good. And you go ahead and you turn this in. Well, one of the tests I'm going to run is I'm going to try this on an empty list. And suddenly your program is printing some bizarre number, right? And if you happen to discover this, right, you might add another layer of code which says, you know, if the number that you're about to print has got some particular property, right? So understand bugs, right? Yeah, I started a bug discussion in chat, I guess. You know, I used to put bugs outside, and somebody swore to me that, like, there's some spiders that can't live outdoors, and that they've actually lived indoors, like, as long as people have been building indoor structures. And I don't know if that's true or not. I looked it up, and it actually looked like it was kind of true. But I don't know if that's true or not. That's a good homework assignment. See if there really are indoor spiders. All right, so I don't know if that's helpful or not, but you know, basic themes, right? Manipulating your linked list by updating, you know, elements in the fields of the node stored in that array. And when you encounter a bug, right, don't just try to write more code to deal with the case, you know, deal with what the bug is producing. Try to go back and understand where the bug is and actually eliminate it, right, instead of patching it. And that's probably the biggest thing to keeping your code from getting, you know, kind of more and more unmanageable as it grows. And for larger projects, we're going to do larger projects here. We're going to do much larger projects in 223. It's helpful if your code doesn't get, you know, more and more kind of unwieldy the bigger it gets. If as you develop your code further, you feel kind of squickier and squickier about it, it might be that you're like trying to fix bugs instead of go back and eliminate them. All right. Questions? Other than about spiders, well, we can ask spider questions too. I don't understand fruit flies. You know, I got bananas the other day. I've got fruit flies in my kitchen. Where do they come from? I never see them in the house until I have bananas out. I understand why people used to believe in spontaneous generation, because they just appear, yeah. I mean, are they like hiding out in the closet saying, I wonder if there's any bananas yet, you go check. And then when the bananas come out, they suddenly appear? Or do they like sneak in through little tiny holes in the walls, or, you know, under the door, or what? Yeah. There's probably maggots in those bananas. Well, it could be. That makes the really good banana bread when you turn those in. I'll go with interdimensional beings better than maggots. All right, cool. I will let you out 30 seconds early. I will see you next time. Keep going with PA1. We're good for ODPs for the rest of the week. So keep going on PA1, and I will see you next time.